Welcome to this session, On-Demand Hydraulic Assist for Vocational Trucks. We have two speakers today, Scott Betzen, as well as Daniel Scott. Scott is actually sharing this, so they're sharing the presentation together. And Scott actually has over 40 years of experience in the fluid power industry. He was starting out working in the fluid power distribution world and joined later on Poclain for the last 25 years. In sales and engineering. He's responsible today for business development and basically developing the road assist drive system market for North America for Poclain. And he's degreed in fluid power technology from Minnesota West Technical College. Also working a lot with IFPE, AEM, and NFPA for several years already as a collaborator in several committees supporting the team and trying to make sure that we get more successors in that industry, engineers, and so on and so forth. Daniel, actually, who's presenting with him, has a master's in mechanical engineering from Purdue, is in the fluid power industry also for more than 8 years, and is the VP of engineering for TDS, Easy Track brand, basically building drive systems for many, many years already in the industry, supporting the on-road industry with basically front axles and drive systems. Okay, so with no further ado, I would like to have the gentleman present. Scott, you start?
Yep.
Wonderful. Thank you very much.
So seriously, thank you for being here. Hope you find this interesting. So we're talking today about on-demand hydraulic assist drive for vocational trucks. And what does that mean? Well, we'll kind of go through why have all-wheel drive in the first place. What types of all-wheel drive exist, mechanical all-wheel drive and hydraulic all-wheel drive. And then we'll compare the different types. And then we'll get into how the hydraulic all-wheel drive actually works. So, what do vocational truck drivers need? Yep. So they need productivity more than anything. That looks like minimized tire wear, fuel consumption, minimize downtime, and also payload. They also need driver comfort. They need to be confident that they can focus on the job and know that they're going to be safe and avoid dangerous situations. So some applications, though, spend almost all their time working in the off-road. And for those kind of applications, they really aren't correct for the hydraulic all-wheel drive. They need to have a heavy, very heavy-duty mechanical type all-wheel drive. But what do the average drivers face? For what we're talking about trucks that spend close to 95% of their time on the road and 5% in the off-road situation. If you look first at the long-haul trucks, that's 100% on-road type application. But our focus, as I said, is going to be on the vocational trucks and then working towards the full-time off-road like we just talked about in the last slide. So again, the on-highway type trucks, very high efficiency on the road, pretty much no efficiency off the road, and then the reverse as we move across the scale. So what we're going to do in the next couple slides is talk about a standard truck, a 6x4 type truck, versus the mechanical all-wheel drive system. So we're showing mobility of the 6x4 either with or without a load. And as you can see, the performance is not that great. We're looking at this obviously in an off-road condition, so it's not that great. And unloaded, it's even worse because it's hard to get traction without weight over the wheels. As opposed to a mechanical all-wheel drive, loaded or unloaded, we have a very good situation as far as driving. But then we look a little beyond what else besides just the driving. There's maneuverability. Turning radius is a big thing. We have a reduced turning radius normally with the mechanical all-wheel drive, so that goes down on the scale. Traction can be an issue, and also ride height changes with the mechanical all-wheel drives. And then, of course, it's a reduced payload with mechanical all-wheel drive because of the fact that there's an axle, a drop box, and a lot of extra weight on that goes on the truck when you add the all-wheel drive system. And that extra weight, as well as the fact that you have some constantly meshing gears, is going to reduce the fuel efficiency as well. And finally, for driver comfort, the ride height and getting up into a higher cab, again, the standard truck wins over the mechanical all-wheel drive. So then, if we look at the hydraulic all-wheel drive, we kind of get the best of both worlds. We have high performance off-road with or without a load. We have good maneuverability because we don't change the turning radius or the ride height, and the payload is a better situation because the weight of the hydraulic all-wheel drive is much less than that of the mechanical, and so along with fuel consumption, and then of course the operator comfort, because it's really just like driving a standard 6x4 without any all-wheel drive. So hydraulic all-wheel drive gives productivity, driver confidence, and safety.
So what components do you have in a hydraulic all-wheel drive? You're going to have a pump, so you need something that's going to create flow. From there, you're going to have electronics, so you're going to need some way to control the pump, know what you're doing, know what the vehicle is doing so that you know how to change the pump command. The valve, so you're going to need to turn or connect the flow from the pump to the motors, and this valve is going to ensure the engagement and disengagement of the motors. And then the motors, you need some way to provide or to have traction, and so you need hydraulic motors. Tank, cooler, filter, hosing, those would all need to be sized according to your duty cycle and the pump and motors that you have on your system. So what does the system look like? Here you will see that here would be the pump. Here would be your combo. There we go. So this application is using an Allison transmission with a PTO drive shaft to power the pump. The wheel end, so the motors are going to have a special knuckle that has porting for the hydraulics to get it out to the end of the wheel where the motor is fixed, and that motor then drives the pump. And the next slide has a little bit more detail on that motor. And then again, the cooler tank combo. So this application has everything built into one package, trying to minimize the space that is required for a hydraulic all-wheel drive on a truck, because, as you know, vehicles don't have a ton of real estate. So adding this system, we're trying to reduce the size of the components. And like I said, the motor integration into the axle. So we have a modified hub and spindle. So you have a standard truck beam with this modified hub and spindle with standard brakes that you would have in the market. And we're using a radial piston cam lobe hydraulic motor. So we have our knuckle here with special drillings that take hydraulic fluid out to the cam lobe motor, and that would be powering in an on state, giving high pressure to have the pistons follow the cam and propel the wheel.
You can do both drum or disc brake.
Yes, drum or disc brake. Again, here just this red being up here in this position. So how does this work? Hydraulic all-wheel drive is basic principle that you're just trying to match the speed flow of the rear axle to this powered front axle. So you have the rear wheels are driven by the engine into your transmission into the differential, and then the front axle is driven by the pump sending flow through the valve to the motors, and you're just connecting the two so that your front axle is matching the speed of the rear axle. So how's this done? Like I said, we have engine speed, our gearbox ratio. So you take your engine speed, you divide it by your gearbox ratio, you divide that by your rear axle ratio, and then you're going to multiply that by the wheel circumference, the rolling wheel circumference, to know what your rear axle speed is. So then when you're trying to match that speed, you have your engine speed, your PTO ratio, so you'll know how fast your pump is going to be spinning, and you'll take the front tire, your pump displacement. So right here you have how much flow your system has at that state, and then you're going to divide that by your motor displacement, and then again by the quantity of motors to know what your speed needs to be there in the front end. And down here, it's, the pump stroke depends on the gearbox ratio, giving you different amount of flow with the different ratios. So how does this all work? In the traction mode, we have a pump that when you turn the system on is going to be connected to the engine. It's going to spin up. The valve is piloted and the motors are engaged, so you now have hydraulic oil from the pump to the motors. The pump is controlled by an ECU to maintain a speed synchronization between the front and the rear axle. So you're going to be changing the...
Our animation is missing.
So that's the last one. Your pump is controlled by the controller to give you the correct amount of flow to match your speed. And there's a minimum pressure set, so you're only going to provide the flow to spin it and maintain a minimum pressure in that forward line. And then oil is removed also on the low end of the circuit in a hot oil shuttle. Yeah, the animation is missing. So the oil is removed out of the low end of the circuit in the traction mode, just so that you can reduce the heat in the loop of the hydrostatic system. So in freewheeling mode, this is where your system is going to be off. Your valve is not controlled. One way you can do this, your pump could be coupled to the engine still, so your pump would be spinning, or with a clutch you could have the pump not spinning anymore. But the pump is not controlled and it remains in a neutral state. So with the pump being connected to the engine, it would be in neutral or off, not spinning at all. The pump is in a bypass position. The charge pump is derated through the valve. So your pump is looped in its own loop, P to T. The charge pressure depends on the engine speed because your charge pressure would be spinning in this situation or off, and the high pressure lines are at charge pressure. The motors are not engaged, and the motors are actually connected so that the A and B of the motor are connected to tank, keeping the pistons retracted in the cylinder block so that you can freewheel down the road and not have any of the effects that you would with a traditional mechanical all-wheel drive.
Let's hope this one works. No, this one isn't working either. We've got animations that don't seem to be working.
What's that?
Animations?
Oh, yeah, they don't work.
Oh.
Sorry.
Okay. Sorry about that. Okay. Okay, good. Okay. So what we're showing here is without hydraulic all-wheel drive, we're on a good terrain on the road basically. So with that, the hydraulic all-wheel drive, the hydraulic all-wheel drive is freewheeling. It's not engaged. I don't know what happened there. Okay. And then we go into an off-road situation. So now we have the rear wheels can start to slip, lose traction, potentially get the truck stuck. So now we engage then the hydraulic all-wheel drive. So we are in assist mode. The traction, we're still off-road, so the traction is limited. And we do have the wheel synchronization because of the hydraulic being engaged. So as Daniel said in the earlier slide, it's proportional, and if the animation were working, you would see the arrows adjusting. And so the more traction you have, the more we would reduce what's happening with the hydraulics. We don't need as much pull. And as you lose more and more traction, the hydraulic does more pulling.
No. It uses the tail shaft speed, knowing the differential ratio and knowing your wheel circumference. It takes it from there and does the calculation, but it is not taking individual wheel speed.
And then even on the road, we call it torque transfer, is still an advantage of the hydraulic all-wheel drive, where it can be giving some assistance, pulling an extra large load or something. It can give you an enhancement to the rear-wheel drive. I think we're back to you.
So what this graph showing here is the engagement, disengagement, freewheel, all different speeds that this system runs at and how it works. So on the bottom here, you can see that at all speeds, if you're in freewheeling, you are fine. The system acts as a two-wheel drive vehicle or a standard vehicle without a hydraulic all-wheel drive. So you do not have limitations in a freewheeling state. Down here is engaged, the engaged speed. So on this application, we have about 0 to 18 miles per hour. And this is based on the vehicle specs, the transmission and rear ratio, tires and all that, for what your actual engaged speed is. So when your system is engaged, you get up to the end of your limit and your system turns off, you would have this disengagement right here. And in that state, it is in freewheeling, but the system is active. So it is waiting to either slow back down, but it is in a standby mode, monitoring all the system parameters. So if your speed were to slow back down in this standby mode, you're going to have re-engagement. So your system will come back, your PTO will shift back on, your pump will provide flow that you need to match your speed. But if you have left a slick situation and now you're on stable ground or going onto the highway, the system also will disengage itself. It'll go to this, from this freewheeling mode in standby, you will hit a certain speed, and now your system is going to shut off completely and not re-engage if you were to slow back down. So it is monitoring the situation and the speed and will turn itself completely off. Most likely you're on the road or heading down the road. So here we have max torque versus the max possible vehicle speed. So again, it is all flow based from the pump to the motors. And so you can have high torque, lower speed applications where you're in the 5,000 foot-pound range, but your speed is going to be limited 10 to 15 miles an hour. Again, all these are based on the vehicle specs, or you can go with a lower torque, either a lighter axle, a lighter truck, or needing to have less tractive effort and go with a little higher engagement speed, closer to 20, 22 miles an hour. And you can see here with these graphs just what that looks like in your torque versus speed trade-offs of the two different motor displacements. And down here showing the two vehicle speeds and the trade-off, and there is an asterisk down here of this is using specific vehicle specs. So these do vary a little bit. So what other benefits of hydraulic all-wheel drive other than just getting you an all-wheel drive vehicle, creep drive mode? So now you are able to use this truck as a hydrostatic drive and drive it with a joystick. So your truck would be in neutral. Your vehicle is driven hydrostatic only. The pump displacement is proportional to the command and the engine speed. So you'd be driving this with a joystick, and you would be regulated by the software in ramps. So you would have acceleration ramps and deceleration ramps all provided in the software with your joystick. And this max grade, max speed, it'd be maybe a trade-off. Again, it's dependent upon the vehicle, the weight of the vehicle, and the specs of the vehicle there. And then boost mode. So another advantage of hydraulic all-wheel drive is this boost mode, where you can give more effort out of the front axle without having to, in a traditional mechanical, you would have to spool the engine up into a higher torque range and then have that front axle, need the torque. But with this, we can change the displacement of the pump to provide more flow, create more pressure, and in turn be more tractive effort, more torque in that front axle. So it would be the same as any of the others. The system would be on. It would be active. The valve is piloted. The motors are engaged. The pump is controlled to maintain the speed. But now in this case, given throttle command, you don't have to necessarily be moving to get this high pressure. So you have max speed for max boost, a max speed overall of the system, and here's your vehicle speed, and then your max boost pressure here on the y-axis. So as your vehicle speed is very slow, but you have a certain amount of throttle command, you may not be moving, but you're about to be moving, and you want as much effort as you can from our system or from a hydraulic system, you would have this high pressure to get you moving. And so as you start to
launch assist,
yes, as a launch assist, you would get moving, and as your vehicle speed starts to increase, you would start to decrease this pressure down to the minimum traction pressure, kind of the standard pressure of the system. So again, this is just one of the advantages of having a hydraulic system where you can change the displacement of the pump to give you these benefits.